Now, in the same way that we were able to take a set of different capacitors and find the equivalent capacitance of all of them acting together, let's see if we can do that for resistors. In the same way, we'll have the possibility of dealing with resistors in series. And resistors in parallel. And in both cases, I've got some change in potential between A and part A and B. Now, for this section, I've got two different elements. So I can look at this and say, okay, the change in potential from point A to point B must be equal to the change in potential over resistor 1 plus the change in potential over resistor 2. And I have Ohm's law to work with, that delta V is equal to IR for a given element, or if I'm able to collapse these down into a single effective equivalent resistance for that, this is true for that equivalent resistance, I can look at this and I can say, okay, the current through resistor 1 has to be equal to the current through resistor 2, has to be equal to some current I. Why does that work? Because, there's no place for the current to enter or leave. The conservation of current says that that's not going to happen magically, which means that if I look at this, I can say, okay, let me take this equation. Delta V from A to B, which is equal to the current I times the equivalent resistance R of the set, is equal to the change in potential over the first resistor, which is equal to the resistance through the first resistor, the current through the first resistor I, times R1, plus the current through the second resistor, same current, times R2, or the equivalent resistance if I divide everything through by the current, which, hey, is the same in each case, then for resistors in series, the equivalent resistance is equal to the sum. Now, that means that if I have resistors in series, the equivalent resistance is going to be as high as it can possibly be. Well, that makes sense. Again, to go through that anthropomorphized model of Timmy the electron, Timmy has to go through every single resistor. There's none that can be skipped. So it's going to get as much resistance as possibly could hope to deal with. Now, let's look in parallel. Okay, I know that the current I from here to the branch point comes back into a current I after they join back together. So that single current through the equivalent resistor has to be equal to I1 plus I2. I also know that the change in potential over resistor 1 has to be equal to the change in potential over resistor 2, has to be equal to the total change in potential over the equivalent resistance, because if I go from point A to point B, it doesn't matter what path I take, the change in potential has to be the same, and if this resistor has a resistance high enough so that we can ignore the effect of the wire, if these are ideal wires, then, the change in potential over the path through R1 must be the same as the change in potential through the path going through R2. So, if I write it like this, okay, the equivalent resistance from Ohm's law is equal to delta V over R equivalent, and that's equal to I1, which is the change of potential over thing 1, which is just the change of potential over R1, plus the change of potential over thing 2, which is just delta V over R2. So, for resistors in parallel, the resistance of resistors in parallel is equal to, 1 over that equivalent resistance is 1 over R1 plus 1 over R2, etc., etc. Or the weakest possible resistance. And that should make sense. Again, going to the model of Timmy the electron, you get to this point, Timmy has a choice. Either being forced to go through R1 or being forced to deal with R2, but not both. Now, let me just freeze the frame, freeze it right here if you want to get all of that, if you need to get something down. Notice that resistors and capacitors behave differently respond differently in series and in parallel. Capacitors work or have a much greater effect if they're connected in whoops. Oh, no. Yeah. Capacitors have a much greater effect if they're connected in parallel, and resistors have a much greater effect if they are connected in series.